But now coming to this afternoon's program, it's a great pleasure for me to introduce Hisashi Okamoto, who I think has traveled the furthest of any of the participants from Kyoto, came especially for the meeting. So it's a great pleasure to welcome him here. And he's going to talk about trajectories of particles underneath water waves. So, please.
Well, thank you very much. Well, it is my great honor to be invited. I have for a long time I have wanted to come to Cambridge, but I didn't have a chance. And I wrote an email to Mark a year ago, and he accepted my invitation. Thank you very much. And I really appreciate it. And today I'm going to talk about this on this title, and but I must apologize first of all. This is not quite new paper. I just want to introduce what I did in these few years. And particularly, I'm going to talk about this paper and this paper. So I'm not going to talk about theoretical aspect of the water waves, but I'm going to report some computation of the fluid particles. Fluid particle computation is quite different from the computation of the velocity profiles or some any other solution of the partial differential equation. So partial differential equation solution is already obtained. And after that, I want to compute the trajectories or orbit of the fluid particles. And that is what I'm going to report. Those are quite important. So there's a famous book by Ottino. This contains a lot of things about Lagrangian chaos or chaotic mixing of the particles. And there are many. But I'm going to talk about very simple problem. You may have known this problem, but many people now don't know this paper. So I want to introduce this paper, written by Maxwell in 1870, Proceeding Random Mathematical Study. Do you know this paper? Is there anybody who knows this paper? Or one? Great. So he considered this kind of problem. There is a cylinder, infinite cylinder. So the flow is two-dimensional, and infinite cylinder is minus infinity in x direction. And it moves in a constant speed, okay? And it passes to the origin is here, and it goes to plus infinity. And then fluid particles here, taking any part of the fluid. So outside of the cylinder is occupied by the fluid, all the fluid. And take any particle here, and he wants to compute the trajectory of this particle by this moving cylinder.
Is it an illicit problem?
Excuse?
Is fluid ideal?
Fluid?
Ideal? Do you have this concept or not?
Yeah. He assumes this is an ideal fluid, so this is incompressible. Yeah, but I'm going to talk about something else too. By the way, sometimes I can't understand English, and I must ask, I'm sorry. So please be patient. I'm living in Japan. And
That's okay, sometimes we don't understand Japanese.
well, but it's difficult to understand the Japanese accent. Okay?
No, that's easy.
Okay, so he considered this problem, and the answer was rather surprising. The answer is the elastic curve. Elastic curve is this thin dot, and this thin dot curve is the elastic curve, elastica, called by Euler. And this is the answer. And that is Maxwell's problem. Let me explain his solution. Because the cylinder is now moving, but let us fix. So I consider two coordinate systems, two systems. One is attached to this cylinder, The other one is absolute coordinate system. So we leave this here, and the cylinder is moving. So this one is attached to the cylinder. So the x and y are relative coordinates, and small x and small y are absolute coordinates. Yeah. Then this is a stream function. You know this. This is because this is implicit, incompressible. Now, this is well known, and the velocity is supposed to be 1, and radius is supposed to be 1. And so the fluid particle moves this way, and that is the contour of the stream function. This is well known. So we know this, and this is written in many, many textbooks. However, in his setting, this is moving. So this red particle is pushed forward to this part, and so on. And answer is this. If the particle is here, when t is minus infinity, t is minus infinity means the cylinder is minus infinity. At t0, this is the point. T comes to the top, particle comes to the top, and then it's pushed forward. At t plus infinity, it reaches this point. So that the point, all the point on the x-axis is pushed forward, and it is large if this is close to the origin. This kind of computation he did. And there's another picture, the same thing, but this one is that I put fluid particles on the y-axis when t is 0. Okay? T is 0. This is put when t is minus infinity. So minus infinity is 0 plus infinity. In this case, minus infinity, 0 and plus infinity. And this is nothing but the elastic curve by Euler. So he found this. This is a scanned image from Maxwell. And I computed this by my PC. And it is amazing that he is such a great technician. I don't think he himself drew it. He had a good assistant or technician. But it's a great picture after 140 years. And now, you consider that this is a kind of, what's that? Trifle. It's not interesting. It's not difficult, maybe. But let me say, this one is a trajectory in relative coordinate. This one, because this one is an absolute coordinate, x and y, they are connected in this way. Obviously, no? So x minus t is equal to capital X. And I have this one and this one. Therefore, you say that if we solve this non-autonomous differential equation, then we have this elastic curve, at least numerically. So it's not a difficult problem. That's true. But I did it myself. This was my result. I solved this ordinary differential equation by longitudinal method with this parameter. So it's about, let's see, 2 million steps. After 2 million steps, from 0, it comes here. And this is the place where the particle approach when t goes to infinity. And if you increase t by, say, this is 20,000, suppose this, I go to 200,000, what happens? 200,000, you go only slightly. Yeah, you after billions, you may come to here, but it's too slow. So you cannot find if this is enough or not. And another problem is because x dot is so small, this one and this one is almost the same. Therefore, that means computationally, there is something and there's something different which is very close, and they are subtracted. That means we may have a loss of digits in numerical computation. So this is not probably a good idea. In my PC, it took 7 minutes and 24 seconds. I computed this by Maxwell's method, and it took only 0.18 seconds. And so Maxwell's method is good. So I want to explain Maxwell's method. Maxwell's idea is this. Because we have, sorry, today I forgot laser point with me.
There's an old-fashioned
There's a
one.
stick
over
there.
there.
Stick if you
Oh, really? This is better than my phone. Okay. This one is a stream function. So this is a constant along the orbit, okay? So this must be constant. I call it the eta infinity. Okay? So this eta infinity is constant. That means x can be written by y and eta infinity. So x is a function of this one there. And I consider now this. This one is now written in some function of y and eta. Okay? Therefore, there is no x here. And eta infinity is a constant. So this is an ordinary differential equation of y, but because it has only one unknown, I can write this in this way. So it's the integral of y in y. And I can write this function explicitly. Then t and x are functions of y only. If that is done, then x and y are functions of y. Therefore, everything is parameterized by y, capital Y only, and eta infinity. But this is given initial data from initial data. So Maxwell considered this kind of problem. And after that, I don't know who is next, but probably Charles Darwin in 1953 considered three-dimensional case. That is sphere, irrotational flow around the sphere. And he considered, yes. This one is a computation for 3 dimensions. And I want to consider something else now. That is other factors like viscosity, Stokes equation, Poisson's equation, or Brinkman's equation. This is a typical orbit in the case where we have viscosity. Now, let me explain what I did. In the 3-dimensional case, I consider a sphere, complete sphere of radius 1 is moving from minus infinity to plus infinity along the x-axis at constant velocity 1. And then what happens? I follow the recipe of Maxwell. Then I found that all the trajectories are unbounded. In Maxwell's case, that was bounded, starting from here to here. But this is not bounded. All the trajectories are unbounded. What does this mean? Okay. Of course, the shape depends on the eta 0 or eta infinity. But eta 0 is a parameter where this particle here at the top, this height is eta 0. Eta infinity is the height at infinity. Okay? So eta 0 is always greater than eta infinity. So if I determine eta 0, eta infinity is determined completely. And if I give eta infinity, eta 0 is determined completely. So one is a function of the other. Now, by the way, this is a streamline or trajectory in the moving coordinate in the case of Stokes. And this is the absolute plane. Absolute plane means a plane of axis symmetry.
Excuse me.
Yeah.
These streamlines that you have which look like waves, do they in any way their steepness changes as the value of eta 0 changes?
Steepness of this one and this one?
Yes.
Yeah, that is what I'm going to explain in a minute.
Very sorry.
Yeah, but that's important. This is rather slow. This one is not. But probably you have already noticed that this curve and this curve, it doesn't change much, almost the same. So looking at this, I realize that if eta 0 or eta infinity goes to infinity, there is some kind of asymptotic profile. Yeah, and I found this. That is this. Okay, so that was this. X is a function of z, and z is this. Or y is a function of x. That is it, given by this. This one. So if I tend, I mean, eta 0 tends to infinity, then this form is obtained. This is it.
What was the eta 0 again? Is that the streamline?
Excuse me?
What is eta 0?
Eta 0 is a parameter. 6 is 6 because it is 6 here. Height, elevation, that is eta 0. And
There's no streamline in this case.
oh, no, because it is equivalent to the non-autonomous ODE. Okay? So this one can be expressed by the stream function, of course. This is well known. Stokes found it. Yeah. But this one, we cannot use that directly. And then many people don't believe me because this one has a non-trivial shape when it goes to infinity. Elevation is infinity. So that means, suppose there is small dust, weightless dust here, and nothing else is moving, but a car is moving at random, at constant speed. But still, it moves this particle by this amount. And I computed this in this way. Oh, I'm sorry, this is it. So the elevation from here to here is about approximately 0.75. So that if the particle is very far away from the car, then 3/4 of the radius of the car is moved. So this dust is moved by that distance. So this is rather paradoxical. It's strange. I can't believe this. But no.
So, but at least in this calculation, the motion is very slow, right?
Right.
So it starts when the car is very far away. So I mean, like a tsunami in some sense.
Yeah.
It's very, very slow
Slow,
motion. So
slow
you wouldn't
motion.
notice it, right?
Of course.
So it's to speak about car, the limit of Reynolds numbers tending to 0.
Yeah,
Yes.
of course. Yeah.
So
But your three-dimensional case is three-dimensional.
There's a three-dimension, axis symmetric three-dimension.
Three-dimensional is symmetric.
Yeah. And yeah, another interesting point is that xt moves to infinity. Yeah? It is unbounded, so it goes to infinity. But the cylinder is moving at a constant speed. But x, the particle, moves in this rate. So it's very slow, very, very, very slow.
Question?
Yes?
Is that the particle that's on the center of the
Yes.
axis?
Yes. On the axis, yes.
And the particles that are off don't do that?
Mhm. Right. And I computed, suppose the cylinder is moving, sphere is moving at 1 centimeter per second. And continue it for 1 year. After 1 year, it moves 315 kilometers, or about 200 miles. Okay, it's far away. And a particle is dragged only by 25 centimeters. So it's very, very slow. So that time scale is quite different.
I'm trying to understand his question. So you said the particle is on the axis, but
No, the particle is away from the axis.
away from the axis.
Yeah. Sphere is on the axis.
All particles move this far?
Yeah,
Particles at infinity all move that
Yeah.
far.
yeah. If the particle is sufficiently distant from the axis, then it is moved by three-quarters of the
Particle has no mass.
Yeah.
Gravitational flow.
Particle has no mass.
Well, it's,
Yes, yes,
No mass.
that's right. Yeah.
Otherwise you would be in trouble.
That's right, yeah. If you consider a very small mass, then story is very different. Yeah, of course. So this is a strange phenomenon.
it's part of the
Yeah.
Yeah, no mass. Otherwise,
Well, it's a fluid particle.
It's a fluid
Yeah,
particle.
fluid particle, yes.
I know.
Then similar problem can be considered for in many situations. I consider this equation, Brinkman's equation, I call it. By the way, this is used for the porous media flow or underground water flow. And recently I found many references which uses Darcy-Stokes to name this equation. Because if lambda is 0, this is Stokes. If lambda is infinity, and forget about it, you should consider this too. Then it becomes Darcy's law. And so, but I don't think this is a good name, because neither Darcy nor Stokes use this equation. Actually, this equation was used by the Brinkman. Yeah. But Stokes used that equation, okay? Navier used that equation. That is okay. But neither used this, okay?
How
Therefore,
can you be so certain?
excuse me?
How can you be so certain?
Oh, I checked many papers. Darcy and Stokes. Stokes didn't consider a thing.
So who's Darcy then?
No. Oh, Darcy is not a mathematician. He's an engineer, and he considered this kind of velocity by the experimental data, I think. He guessed. He's guessed. He's not a theoretician. Well, anyway, a Dutchman called Brinkman considered this equation in 1947. So I want to pay respect to this Dutchman, so I call this the Brinkman's equation. Well, if lambda is very small, it is very close to Stokes. If lambda is 0, exactly 0, we don't have a solution because of the Stokes paradox. So we have no solution outside a moving cylinder. So that's the problem in 2-dimensional. 3-dimensional, okay. We have Stokes' problem, which I showed just before this slide. But this has many applications in underground water. So one of my friends in Tokyo considered this for his experiments. And that is it. In stream function, the partial differential equation becomes this, and boundary condition is this, and it has asymptotic behavior as y goes to infinity. And the solution is this. This one is expressed by Bessel functions. But it's not very convenient. So I compute this in my PC now. I have this. If this function tends to 0, if lambda tends to 0, it tends to the Stokes equation. But the solution does not approach, it diverges. If lambda goes to infinity, the partial differential equation tends to irrotational flow. Now, for this, it depends on the lambda. Lambda 0, 1, and 100. And for particle velocity, if it is very far from cylinder, then it has self-intersection. Otherwise, it has no self-intersection. So if the dust particle is far away from the cylinder, then it looks like an irrotational case. And if it's close to that one, then this one, so the trajectory has no self-intersection. So there are many cases. Lambda and eta 0 are changed. So many. But at least they are bounded. It is bounded. And so similar case can be considered. But I stop here because the technical detail is not so interesting to me, to you, I think. So summary is this. This was considered by Maxwell, two-dimensional, and this is irrotational. This was considered by Charles Darwin. There's no flow here because of the Stokes paradox. Three dimension, I showed you the picture. The Brinkman is somewhere between this and this. So this and this are connected by Brinkman's equation. And Maxwell's idea can be used to any cases. And summary of my first part, excuse me.
Can I go back one
Yes.
second? So, in the 3D, the Darwin solution, it's not, is there, as you go far from the particle, the solution goes to what?
Goes to 0.
Goes to
point,
0.
Single point.
Goes to a single
Yeah,
point. Okay.
Maybe I should
Yeah, no,
have.
I don't remember seeing that.
Yeah.
Okay.
I'm sorry. I'm sorry. Yeah.
Yeah, I guess it's that.
Yeah. So if this goes to infinity, this goes to infinity, and it's the radius. It's almost circular, but the radius becomes smaller and smaller. So that there is no paradox here. It exists only in Stokes case. So I reported this. Many problems can be considered. For instance, many objects or some object in channel. And I didn't consider object or obstacles of general cross-section or any shape. But perhaps asymptotically, we have the same result, I hope. But I have no proof right now. Now, I want to consider a similar problem for water wave. So this is the preliminary part. I consider a similar problem in water wave. And I do not explain what is a water wave because everybody here must be expert on this. But let me say one thing. Because in any case, a mathematician or physicist, majority of people believe that the wave is just moving here and here. So that wave in the stadium is that you are sitting here, and wave came here, and then and stand there. This oscillation up and down is a wave. But in the water wave, this is not the truth. I think you know this. Let me explain by mathematical terms. I assume two-dimensional, irrotational. I'm sorry, I do not consider three dimensions. There are many experts here. But the three-dimension problem must be more complicated. And the traditional setting, irrotational, incompressible, no viscosity, like that.
I think your microphone has fallen to the ground there.
Right.
You might step on it and destroy it.
Okay, thank you. And this one has many stationary waves. A stationary wave can be computed as precisely as you like by computer. Of course, you know the partial differential equation, so I do not waste time for explaining partial differential equations and boundary conditions. But there are two parameters, which is one is related to gravity, the other is related to capillarity, this one I call P, which I name Q. T is surface tension, C is the propagation speed of the wave, L is the wave length, M is the density of the water, G is gravity. Then I can compute the solution. Numerical method I skip. There are many solutions, but I begin with the special case, which was discovered by Krapper. Krapper's case is that we do not consider gravity. Gravity is neglected. But surface tension is positive. Only if surface tension is a force, acting force. Then we have this kind of wave profile. In relative coordinate, we have this kind of trajectory. Each are trajectory of particles. Let's see, I think because we have two speakers, so I should stop a little before 3 o'clock. Yeah. So that means
But we're all friends here, so if you go in a few more minutes, it's not so critical.
I know the next speaker.
Well,
Okay, but at least I must speak about the contribution by Stokes. Stokes considered this problem, and if the amplitude is small enough, if amplitude is 0, that was considered by George Green. This Green's paper was generalized by Stokes, and he obtained this kind of approximation, where A is the magnitude of the amplitude of the wave. If A is very small, this one is small, so we can neglect this, then this is a function. So it means after one cycle, it comes to the original point. But because of this, it do not stop at the original point, but it was pushed forward by the wave. This term. This is called Stokes drift. And drift was computed by Stokes. By the way, Stokes computed this approximation very accurate. I checked it by my computer. And let's see. This is called Stokes drift. I have, this is kind of, so there's a wave. Wave is moving this way, okay, in a constant speed. So after one cycle of moving, the particle on the top of the wave moves in this way. So it's rather big on the top. Near the deep waters, it is almost circular. So it comes to the original point, nearly. So this kind of phenomenon occurs. Therefore, I think it's better to explain by this gravity wave. So this you know very well. So gravity wave it is. So at t0, particle is here. Okay? Then after it goes to here, this one and this one is wavelength. Wavelength is 2 pi in my case. Okay? So about 6.28. It comes here. So this is a picture in the relative coordinates. This one is a picture in the absolute coordinate. In the absolute coordinate system, in the deep water, it moves like almost circular. Almost circular, but not exactly. It is pushed forward very little, a little bit. In this case, it's moved by probably 1/4 of the wavelength. And this kind of wave is not so big, not very big. So you can observe this kind of gravity wave probably in the lake. Therefore, Stokes drift is not negligible. It's rather big. I suppose it's rather small, but it is rather big. And there are some experiments for this, which is very close to my computation.
Sorry to interrupt.
Yes.
Could you just say what the level 0 is? Is that definitely the top of the wave?
This is top of the wave, yes.
Great, thank
Yes.
you.
20 years ago, one of my friends said, video should be used because it says 10 times more than you can say by text. Okay? So this is a fluid particle, red one. And excuse me?
Is it in deep water?
Yes,
Deep-
deep
deep
water.
depths?
No bottom, yes.
No bottom.
Mm.
So
Deep
this
water.
This is almost maximum. What
Not
is it?
very far from the maximum. You're right. Yeah.
Point 42.
I can't remember the parameter, but it's not very far from it. It's a large wave. Therefore, so this is my computation. Okay? And Have you ever seen this before? Good.
But this is very different because here we have a bottom.
Yes, yes.
That makes it very
Yeah.
different.
So this, there is some elliptical
Yeah, but there is viscosity also.
viscosity also. Yes, you're right. But the point is that there is no closed orbit here. Orbit is not closed. Therefore, Gerstner, I skipped this, I'm sorry. If I consider capillary gravity wave, there are many, many interesting solutions. If I consider this one, then particle trajectory is something like this. This one is repeated many times. Then this is a trajectory of the fluid particle. Another one, I skipped this. Well, you can play with the computer in this way for a long time. You can find many, many trajectories. And actually, I use this for my class in mechanics. Let's skip this. And there are, of course, another experiment. This one is the old one in 1979. Recently, this experiment was done in Taiwan, and the result was reported in Fluid Dynamics Research, which is a Japanese journal. And I talked to Konstantin, who is now in London. He proved that all the trajectories are pushed forward. So all the trajectory in the waterway do not close. So he proved this mathematically. And mathematical proof involves the qualitative theory of the dynamical system. And so this is the x coordinate. And if x coordinate is different at 0 and 2 pi, for any p and any gravity and any capillarity, this is a theorem. And Konstantin and his group proved these theorems in many situations where depth is infinity, depth is finite, water wave, rotary wave, so many cases. But I found that if I use the conformal mapping, then their proof is, my proof and their proof is different, and my proof is, becomes rather short, because I use the theorems of the conformal mapping theorem. Then I found that, and also my theorem said, the drift distance is from here to here, okay? From here to here. The drift distance is monotone, decreasing in y. So if y goes this way, then decrease. So my method simultaneously proves this property too. So that is one kind of advantage.
And this is proof for deep water only, or
Oh, no. Or finite depths too.
finite depths too.
In a wave tank, that's not true.
Maybe.
Because you do something very important when with the initial assumption,
That
the
is.
stream function,
Eh?
because you don't allow for a net zero force. Because here we have a force which pushes
Oh,
on the
that
particles.
is.
So you have
I'm
a force
assuming-
and external
yes.
force.
External, that is,
Yeah.
I'm
So we have
assuming
very careful
periodic
measurements
wave. Yeah.
of the highest finite depth waves, where that second line there, monotone decreasing in y, is violated.
No. Oh.
It flows
Yeah.
back, so the net is zero.
No, 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 no.
No, but I mean, so it's
What that you mean?
in reality,
Mm.
this is not.
Of course.
But you don't care about reality.
Yeah, of course, I do not care. I must say, I'm assuming a periodic wave. I'm not considering a wave time
Yes.
experiment.
No, but in real life, that will never occur because you have radiation stress.
But the assumption is different.
yeah,
Sure.
yeah, they go through
Yeah.
the
So you can't make a periodic wave. You gotta get your
Yeah.
skates on and make them because it is
Yeah.
the
Yeah.
most fundamental thing we are
No, you
doing.
get bored after a while or you get exhausted.
You think so?
Anyway,
No, okay, so then
Yeah.
You have to make periodic waves.
but anyway, what I'm saying is that I assume this way. I assume this. Then this is a conclusion. This is true. No, I'm not saying nothing about the wave time.
no, reality.
I'm not saying reality. I'm saying
Wave
mathematics.
is not reality.
Yeah.
So you have a force pushing you.
I know. I know.
Net force.
It's so hot and then we
Yeah,
have.
I want to finish my talk. I want to summarize this way. I begin with Maxwell's problem, and I consider a similar problem for water wave, and non-closedness of trajectories approved in a different method. But I neglected vorticity, of course. I neglected many aspects. If I consider these more realistic property, then we may have a different theorem or different result. These are reported in this paper. Thank you very much for your attention.
Any further questions? Yeah, Ben.
An obvious question, maybe.
Sorry, question
Yeah,
behind you
sorry.
first.
So for the Stokes wave, you find the trajectory really close to the biggest one. How close do you get to the crapper? Do you know what the biggest crapper wave looks
Oh.
like?
I have a, I'm sorry. Crapper's wave is this.
Or sorry, not crapper, Wilton.
Oh, Wilton?
Yeah.
Wilton's ripple?
They're all here.
There's two.
They're all
It's close to the largest one.
With
I mean-
bubbles at both places.
Yeah?
Yeah.
This is a Wilton ripple, yeah. And it is just before the intersection begins. So it's quite big, I think. Yeah. So yes.
Yeah, would you be able to do away without any net force and try to actually single out the backflow?
But can I ask for what you mean by net?
Yeah,
force?
can we ask what effect is he?
What do you mean by net force?
Yeah. The radiation stress is pushing the particles to. I mean, if there is flow, net flow in net drift in the top, it's a net backflow in
Yes.
below.
Yes.
Yeah, and the integral is zero. But here is only forward. So the question is, can you make that condition, which is always observed in reality,
Yeah.
because this is very artificial.
Mhm.
This is theoretical.
So that this flow ceases to be irrotational, and in the framework of irrotational flow, you cannot do this.
Yeah. I think you're right. Yeah. I use a conformal mapping.
Yes.
Yeah. If the rotation is very simple, like shear flow, constant shear flow, then we can add conformal mapping flow and this shear flow. Then we can do probably, but
With constant shear, you could repeat all your
Mhm.
what you've done.
yeah. But so probably that is beyond the limitation of my method, I think. Yeah. Also beyond my limitation is the three-dimensional case. In three-dimensional water waves, you have many examples, I think. And then, have you ever computed trajectories? Maybe there is something interesting, which I cannot do right now.
You know, there's this alternative theory of Stokes drift in the generalized Lagrangian mean. You know about this?
No, what is
Okay.
it?
That's why It's kind of a mixed Eulerian-Lagrangian
Uh,
point of view. I was wondering if you.
Yeah, so but this problem could have been treated in Lagrangian framework from the very beginning, and that would be kind of more natural, yeah.
But he did it right.
Yeah, it's perfectly right.
I chose this because this is very convenient for computing.
Yeah, sure.
Yeah.
Sure, and it's very clean and straightforward.
You know, there is a class of solutions that's recently been discovered called viscous potential flows.
Viscous potential flow.
Yeah,
Oh.
by, myself and Daniel Joseph also.
Oh, Dan Joseph.
Yeah, I put his name because it's probably become more credible than this audience.
I see.
Who the hell are you?
I see.
But that is very interesting because the solution satisfies the exact Navier-Stokes equation, yet it is potential. In fact, he's written a book on it by Cambridge University. It's called Viscous Potential Flows.
I see.
Now, I was wondering whether you have ever considered the trajectories as those types of
Mm-hmm.
Have you tried any?
No, that sounds interesting. Yeah. Thank you.
So with this kind of with this approach, can you now do things like calculations of transport of an object on the water surface, say over the Pacific?
If my assumption is permitted, I can do that. Well, actually, there are many people in Japan who computed this kind of things, particularly because there are many objects which is departed from Japan to North America by the earthquake.
Yes.
There was some soccer ball, there were some boats, fishing boats, and they all the way to the. They believe that is caused by the current or stream, ocean current.
Yes.
But the ocean current does not explain everything. There is a drift, but that's what wave too. So I think there is some small contribution for that.
So do you have an estimate what the importance is of the Stokes drift in this?
I'm not saying so. There might be a possibility.
Oh.
That is what I say. I must be careful.
Okay.
Okay, then, thanks once again. We'll take a 5-minute break.
In the book, so looking over current. Yeah.
Thanks. Very nice. The trouble is, this is more like sitting in a cinema, isn't it? So you know, watching a film.
So then what are you measuring?
No, you realize.